White holes. What are they? And are they the opposite of black holes? If a black hole traps everything that crosses its horizon, a white hole is the time reverse. Nothing can ever go in, only out. So what are they really? In general relativity, the maximally extended black hole solution includes a partner region, mathematically like a mirror that forever expels matter and light. Unlike black holes formed by collapsing stars, white holes have no accepted formation path in our universe. They might require special initial conditions or quantum gravity tricks we don't yet understand. If one existed, it would look like a brilliant outflow with no way back in. An event horizon you can approach, but never cross inward. Sounds like the opposite of a black hole? In a mathematical sense, yes, time reverse behavior. But in physics practice, not quite. Black holes are stable end states. We observe them in X-ray binaries and with gravitational waves. White holes appear violently unstable. Tiny disturbances could trigger them to collapse or never form. No telescope has found a confirmed white hole. No spectrum, no repeating signature, no ringdown. Some ideas link them to wormholes or early universe quantum bounces. Intriguing, but unproven. What would we look for? Sudden, one-way outbursts with no feeding source, constrained by relativity. So, are white holes the opposite of black holes? Mathematically, they mirror the equations. But in our observed universe, black holes are real. White holes remain hypothetical. Opposites on paper, not in the sky. At least so far. Next, we'll ask how they could form, what signatures to hunt, and how to test the idea. We start with horizons, what we can see now and what we can ever see. 3 ideas: past light cone, particle horizon, event horizon. Keep those in mind as we connect them to white holes. Your past light cone is all light that has had time to reach us by today, from nearby stars to the ancient afterglow. The particle horizon marks the farthest distance we can see right now, the edge of today's observable universe. The event horizon is different. With dark energy acceleration, it limits which signals can ever reach us in the future. Cosmology's long-term boundary, not a local object. No edge, no wall, just limits set by time and expansion. Horizons mark reachability. White hole horizons, by contrast, are local general relativity surfaces. Redshift gives distance intuition. As space stretches, wavelengths stretch. Outflows that escape into the cosmos fade and redden as they travel. Some galaxies recede faster than light, allowed because space itself expands. Emission from any far white hole outflow would ride that expansion too. Think Hubble flow plus small peculiar motions. Horizons depend on global expansion. A white hole outflow would simply drift with the flow once free. Light emitted today from beyond the event horizon will never arrive. A white hole flips the local rule. Its horizon can be approached from outside, but never crossed inward. Only emission escapes. Draw the cones. Past light shows what arrives today. Future light shows where our signals can go. A white hole is a local patch whose outgoing rays stream outward, never admitting entry. In an accelerating universe, the event horizon is finite in proper distance, a hard limit on future contact. That's cosmological. A white hole horizon is a compact object boundary from GR. Redshift tracks distance because expansion adds with time. Any escaping outflow, white hole or otherwise, will redden and dim the farther it travels. Peculiar velocity adds small scatter, but the horizon story is set by expansion history. A white hole signature would be one-way eruption without signs of accretion. Combine redshift with expansion models and we map the observable sphere, our particle horizon today. Within it, any local white hole outflow would be visible only as emission. Inside that sphere, structure stands out. Voids, filaments, nodes, the cosmic web we actually observe. A hypothetical white hole would live somewhere in this web. Denser walls and superclusters glow in surveys. Emptier regions fade. We'd search for transients that pour out matter and light without any feeding source. Laniakea, Virgo, Perseus Pisces, flows and basins we infer. Any candidate must fit with these environments and obey energy and timing constraints. Key idea: no cosmic edge. Horizons are about signals. A white hole horizon is a time-reverse cousin of a black hole. Local, emitting, never emitting. Today's map, set by the particle horizon. Tomorrow's contact, limited by the event horizon. White hole physics, if realized, would be near-field GR, not a cosmological border. Emptier regions don't change the concepts. They sit within our cones. A white hole hypothesis doesn't require special large-scale topology. Geometry and statistics favor an event horizon with acceleration. GR also permits white hole solutions, but they appear unstable and unconfirmed. Labels help, but they aren't borders. Particle horizon, event horizon, past light cone. Keep the distinction. Cosmological horizons versus local white hole horizons. So what sky signatures would betray a white hole? A brilliant one-way outflow with no infall, no accretion spectrum, and no repeating feed, constrained by relativity. That is the hunt. This chapter is about formation and stability. In the maximally extended Schwarzschild solution, a white hole region appears, the time reverse of a black hole region. But that's mathematics, not yet a mechanism. The extension includes a past horizon that only emits. Nothing can cross inward. It's the mirror to a black hole's future horizon that only absorbs. But math does not guarantee formation. Stellar collapse makes black holes. In our universe, no accepted process naturally produces a white hole. Classical stability is the problem. Tiny infalling disturbances blue shift enormously near a white hole throat, likely triggering collapse and erasing the outflow. Unless initial conditions are exquisitely fine-tuned and perfectly quiet, a white hole region should be short-lived, if it forms at all. Speculative idea 1. A quantum gravity bounce. A collapsing core could avoid a singularity and re-emerge later as a white hole-like outflow. Idea 2. Late-time remnants. An evaporating black hole might transition to a brief white hole phase that releases stored information. Evidence status, unconfirmed. Idea 3. Wormhole-like constructs supported by exotic effects. Interesting hypotheses, but still hypotheses. No observations yet demand them. Even if formed, interaction with ambient gas, photons, or gravitational waves would likely destabilize the throat. Classical collapse wins quickly. To persist, a white hole would need special initial conditions or exotic matter that violates usual energy conditions. Requirements we have not seen. What would we look for? A sudden one-way outburst with no feeding source, brief, high-energy ejecta obeying relativity, with no inflow signature. So far, transients, GRBs, tidal disruptions, active nuclei, show feeding or spectra consistent with known engines, not white hole behavior. Bottom line, white holes are mathematically permitted, yet physically doubtful. Formation is unclear, stability is poor, observations are empty. The expanding, low-density universe adds another hurdle. Disturbances are everywhere. That makes long-lived white holes even less likely. We keep the labels clear. Theory shows possibilities. Evidence must decide. For white holes, the evidence remains absent. Future tests, high-cadence surveys and multi-messenger triggers, photons, neutrinos, maybe gravitational waves, coordinated to catch one-way bursts. Wormhole shortcuts or ER-EPR-style ideas remain speculative frameworks, useful to think with, not yet things we can point to in the sky. Multiple lines agree on the verdict. Classical instability and missing signals outweigh the allure of the equations. Prudence says, keep white holes on the hypothesis shelf, clearly marked, until data forces an update. Curvature, topology, bounces, remnants, wormholes, interesting paths to explore, all labeled conjecture for now. We separate map from margin. Robust results here, plausible extensions just beyond, bold ideas placed farther out. As we push farther, certainty fades, but the logic of gravity and expansion still guides the search. Tomorrow's instruments widen the test. Deeper time, sharper statistics, ready to catch the rare, if it exists. For now, white holes sit as elegant possibilities without footprints, awaiting evidence. Hold the distinction, equations versus reality. Next, we return from theory to observations that shape our cosmic story. What would count as a white hole? A brilliant one-way outburst, matter and light rushing outward, with no sign of anything falling in. No accretion disk, no fueling stream, no periodic feeding, just a short, outward-only causal structure that quickly fades. Contrast that with black holes. Hot accretion disks glow in X-rays. Jets fire along spin axes, and inflow leaves clear spectral lines. We also hear mergers. LIGO Virgo Kagra record black hole ringdowns. Clean damped waves after coalescence. No white hole ringdown has been confirmed. A white hole spectrum would be transient and sourceless. Sharp outflow lines without precursors. No disk variability, and no late-time fueling. We check transient catalogs, GRBs, FRBs, supernovae, tidal disruptions. None show a strict outward-only causal pattern without a feeding source. Radio arrays scan the sky for fast one-off bursts. Multiband follow-ups look for disks, jets, or host galaxies that would imply inflow. A true candidate would show outward ejecta without accretion signatures, no repeating engine, and no late fallback glow in X-ray or radio. Most explosive events we see arise from engines we understand. Collapsars, mergers, magnetars, each with inflow, a host, or a remnant. Spectral timing tests help. Accretion flickers and broadens lines. A white hole outburst should lack those inflow fingerprints. Theory adds caution. Classic white hole solutions look violently unstable. Tiny disturbances collapse them or prevent formation. If quantum gravity allowed brief white hole-like bursts, they'd still need a clear, sourceless profile across bands and messengers. So far, no confirmed spectrum, no host-free ringdown, no repeatless, inflowless light curve that survives scrutiny. Meanwhile, the large-scale map holds. Filaments and voids grow from tiny ripples. No white hole imprints are required to explain it. Our neighborhood fits the pattern. Ordinary structures, ordinary statistics. No outflow relics demanding a white hole nearby. Black holes, by contrast, are observed. X-ray binaries, EHT images, and gravitational waves. Multiple converging lines of evidence. The CMB and galaxy surveys fix geometry and growth. Near flat, expanding, with no need for white hole features in the data. If a white hole appeared, we'd expect a one-off, host-ambiguous flash with outward ejecta and clean, sourceless timing. We'd stack spectra, compare light curves, and search for neutrinos or gravitational waves. All tests a white hole burst should likely fail. Simulations and instruments keep improving. Null results still teach, tightening limits on any white hole-like phenomenon. The principle holds: measure first, infer later. Black holes, yes. White holes, still hypothetical. Keep watching the bursts, the spectra, the waves. If a white hole ever speaks, it will speak outward only. And we'll be listening. How would we find a white hole? Start with transients. Sudden, brilliant outbursts with no detectable progenitor and no inflow. We look for one-way energetics, fast rise, hard spectra, and fading tails, without accretion lines, precursors, or feeder disks. All sky monitors flag candidates. Robotic follow-up checks for a hidden engine, supernova, TDE, magnetar, before anything exotic. Rubin's LSST sweeps the sky with rapid cadence, tiling, differencing, and alert streams to catch short-lived unbound blasts. Roman adds deep, stable imaging, precise light curves and colors to separate true one-way outflows from lensed repeats or AGN flicker. Multi-messenger triggers matter. Photons, neutrinos, and gravitational waves. Coincidences test whether energy escapes without an infall partner. Ultra-high energy cosmic rays and gamma ray limits constrain any putative outflow. Hard spectra and anisotropy would betray odd, one-way engines. Neutrino observatories, IceCube, KM3net, watch for bursty, direction-aligned signals without optical progenitors. GW detectors provide siren-style distances. Paired with sky maps, they fix energetics, key to ruling out mundane explosions. Candidate vetting is minimalist and strict. Context imaging, spectra, host search, lensing checks, and environment flags. We test light curve shapes, color evolution, and late-time tails. Most imposters fail. Supernovae, TDEs, and AGN variability. Standard candles and rulers set distances and lensing, exposing misclassified brightness, dust, or geometry that might mimic anomaly. Cross-checks matter. Candles with sirens, BAO with lensing, independent paths that break biases and tighten the map. We inject synthetic events to measure completeness. Cadence gaps, weather, and trials. Factors are tracked, not ignored. Rapid follow-up across bands, radio, optical, X-ray, gamma, looks for the missing feeder and maps any ejecta. Alert networks, GCN, SIMA, snooze, broker triggers so teams can confirm or retire a candidate within minutes. Radio arrays test for jets, KSZ and afterglows probe outflows, signals that should appear if energy truly escapes one way. Lensing and geometry checks guard against lookalikes, time delays, repeats, or micro-lensing masquerades. Each method sees differently. Agreement is the point, overlap that shrinks uncertainty and corners the truth. Open analyses and shared calibrations keep biases visible. Uniform pipelines, reproducible cuts, transparent null tests. Status today: no confirmed white hole-like event. Every strong candidate so far reduces to known astrophysics. Precision is earned. Cross-calibrated bands, repeatable reductions, open tests. Evidence first, story second. Upper limits improve as surveys grow. Systematics are small, tracked, and folded into confidence bounds. Even without detections, patterns constrain theory. How bright, how fast, how rare such one-way outbursts could be. Next-gen maps, Roman, Rubin, and the SKA, will widen the sky, deepen time, and sharpen every cross-check. Bottom line, no detections yet. Upper limits tighten quickly. If a white hole bursts, the network is ready to catch it. Cosmic expansion accelerates. LCDM's dark energy stretches space faster with time. White holes aren't required by this picture. That acceleration draws a cosmic event horizon, a causal limit to two-way contact, shown by arrows that never meet beyond the line. Our observable radius grows with age, yet the communication horizon stays finite. The future we can ever reach is bounded. Picture light cones. Past light falls in. Future light from us spreads out, but only inside that horizon. Causality drawn, not guessed. The edge is time-dependent. Some galaxies we see today will slip beyond all future messages we could ever send. Their light redshifts and fades toward whispers, then silence at future infinity. Gravity keeps the local group bound. Beyond it, groups drift apart as space grows between them. Don't confuse horizons. Communication horizons in cosmology differ from black hole or hypothetical white hole horizons, global versus local. We may still see ancient light, but no future signal can bridge the widening gulf. On long timelines, billions then trillions of years, the distant web freezes from view. Islands of gravity remain. We measure this now with supernova clocks and baryon ripples, evidence that expansion accelerates. If white holes exist at all, they would be rare and transient. Our dark energy future doesn't need them to unfold. Thermodynamics still holds. Globally, entropy increases. Any white hole outflow would carry disorder outward, not erase it. Black hole evaporation may release information slowly. Speculative white hole remnants appear in some models, but none confirmed. Communication becomes parochial. No known process, white holes included, rescues long-range contact across the cosmic horizon. Yet the observable sphere still grows. Ancient light drifts in from just within the edge. No exotic engine is required. In Penrose terms, the boundary is a moving line in time. Signals end at future null infinity. Local oddities don't change the global sketch. Timeline, acceleration today, isolation later. Islands endure while horizons widen then empty. White holes, if any, would flare and fade. Meaning now, measure well while the sky is rich. Calibrate, compare, preserve. Keep an eye out for odd, one-way outbursts. Our place is a small island with long memory, connected for a while, then mostly to itself. Hypothetical white holes, if real, would be distant and brief. The edge recedes as the night deepens. Keep the lights, keep the maps, keep watching, opposites on paper, evidence in the sky. After the fires, the sky cleared, and we return to our question. Are white holes the opposite of black holes? Mathematically, yes. White holes are time-reverse solutions of the same equations. Physically, not so. Black holes form and persist. White holes appear unstable and unmade. A cosmic hole here is just an underdensity, not a white hole. Our quiet lane sharpens the question, and our instruments. We test ideas against light, maps, comparisons, and repeatable checks. Telescopes under dark skies track stars, gas, dust, where energy flows in, not out. Evidence we'd need: one-way outflows with no feeding source and no inward crossings. Clean spectra, sudden outbursts, and no accretion signs, consistent over time. We also watch motions, flows along filaments that do show feeding. Gravity gathers, matter falls in. White hole behavior would be the reverse, and rare. Predictable trends make anomalies stand out. Nothing conclusive so far. We probe for odd tides and unexplained accelerations. None demand white holes. Step by step, define a signature, search, and cross-check. Quiet regions fit the Webb's statistics. No hidden ejection fountains. From local stars to deep surveys, the picture stays consistent. We are a small light between larger lights, and careful with our claims. Awe invites care. Patience guards against wishful physics. Structure weaves us in. It does not point outward from a white hole mouth. With each distance and flow, the null result grows stronger. Work remains. Quiet. Cumulative. Falsifiable. Observatories keep watch. New alerts test new thresholds. Each survey knits another thread and tightens the net for odd events. Evidence first, then story. White holes remain a story waiting for evidence. Tools span parallax, candles, lensing, waves, and time. As the map expands, hypotheses shrink or survive by test. Across epochs, gravity writes inflow, mergers, and ringdowns, not outbursts from nowhere. Patience is coded into the sky and into good inference. Variety blooms where structure allows. Nothing points to a persistent expeller. Here, life learned to look up and to doubt its first answers. Time is the medium. Attention is our tool for ruling things out. Causes and consequences, traced by light, motion, and now gravitational waves. We keep warmth by knowing where we stand and what we have not seen. Humility first, measurement next, conclusions last. We read the past to predict rare signatures and set traps for them. That we can do this at all is astonishing and grounding. We are witnesses and stewards of methods that outlast fashions. Curiosity builds instruments. Care guides what claims we make with them. We read tomorrow in today's light, and in its absences, models meet rock, spectra, and time. Evidence decides again. Across scales, the record shows inflow, collapse, and merger. Black holes we can weigh. Detectives of the cosmos, caretakers of a home still healing. This isn't only observed, it's lived and shared. Wisdom is choosing to measure well and act on what survives tests. Each discovery deepens awe and responsibility. Our task is grand and patient. Timescales dwarf us. Attention still matters. Feeling small can sharpen purpose. Beauty and truth travel with duty. Tonight, Earth's blue glow rests in a wider dark. Far beyond, stars forge and fade. Quiet engines we can model and test. Endings and beginnings frame our place and our standards. Near-term searches. Rubin for fast transients, Roman for deep maps, SKA for radio bursts, LIGO Virgo Kagra for waves. What would convince us? A persistent outflow with no inflow. Seen, checked, repeated. Status today. Black holes. Observed and stable. White holes. Hypothetical and likely unstable. Opposites on paper, not in the sky, so far. Still, we keep watch. New missions tighten limits and widen context. Tonight's light carries memory and direction. Data leads. Recap. Time reverse math, unstable physics, no confirmed signals. Pull back. From our dot to the web. Questions become tests. Tests become maps. The answer, for now, white holes mirror equations. The universe shows black holes. Hold this sunlit instant. Measure it well. Curiosity guided by measurement. We live in a cosmic hole on a small light. Keep watching. Beyond the edge lies tomorrow's test.